Hello everyone, welcome back to another video. Today we will be looking at support vector machines, or in short they're called SVMs. Now SVMs, people usually have a lot of confusion regarding these. They usually think that this is some kind of big massive subject which you have to learn with some complex algorithm. Nothing like that. I will make it extremely simple today. We'll try to understand what is happening behind SVMs. This is going to be like an intuitive explanation, so we'll understand the why behind the SVMs and all. So yeah, I think let's just get started. SVMs are used in a lot of places. SVMs are used in places like image recognitions. Okay, they're used for text classification. It is used in many places like medical diagnosis, financial forecasting, and etc. But what exactly makes them special? Why do data scientists love them so much? So that's what we're going to uncover today. Basically, at its core, SVM is basically a way to find a best way to separate different classes in the data. So what does that mean? Let's just take an example. Let's just say you have a data like this. You have a bunch of X's and you have a bunch of O's. Okay. So if I were to tell you to separate this data, you would actually draw a line like this, right? And then you would say, hey, this line would separate the two classes. But what if I say this line also separates these two classes? Yes, that is true because every part of one class is lying to the other side of the line and the other part of the other class is lying to the different side of the line. What if this is also a way to classify this uh, to separate these both classes? Yes, that is also true because we are not doing anything. But out of these three lines, which one do you think is the best one which can classify both the classes? You can decide how the best one is by using SVMs. So before we go into all of these, I just want to tell you about very some basic key concepts which you need to know before you hop onto SVM. Okay, the first thing which we'll learn about is called as a hyperplane. Now, don't let this fancy name intimidate you. A hyperplane is just a decision boundary that will separate data into different classes. Okay. So let's just take the same example which we've seen here on the canvas. Hyperplane is simply a line which separates my blue dots from the red dots. That is it. Okay. And in this is since this is a two-dimensional space, you can say that this hyperplane, whatever we're trying to do, is a line. Yes. But if it is a three-dimensional space, that means if you add an extra dimension here, this line would become a plane. Okay. So in that case, if you have n dimensions in your data, your hyperplane would be of n minus one dimension hyperplane. So that means if you have like 100 features, your hyperplane will be 99 dimensional. We can't visualize that, but basically the math will work in the same way. Now, once you have this hyperplane figured out, the classification of data is very simple. You just, whenever a new data point is being added, just see if it lies to the either side of a hyperplane. Let's say this is the optimal hyperplane we have. If the newer point is being shown here, you would see that it is lying towards the other side of the hyperplane. So I would just classify it as an X. But if it is lying to the either side of the hyperplane, you can just classify it as an O. As simple as that. Now I hope you got the idea of a hyperplane. Let's just see what another concept is. It is called as a margin. Now what exactly is this margin? Let's take this example again. What exactly is this margin we are talking about? Let's just remove some points so that we can have a proper representation. Now, in order to divide these classes, I can have a few lines passing through this. This is a line which can divide these two classes. This is also a line which is dividing these two classes. This is also a line which is dividing these both classes. But what exactly do you think is a perfect line which will divide these classes? Of course, it's this one, the one which I'm trying to highlight right now. This one. Why? Because it has a maximum margin, right? Margin is the distance between the decision boundary and closest data points from each class. So this is the closest data point of the red class, and then this is the closest data point of the blue class. Now the margin is the distance between the closest data points and the decision boundary. And these parallel lines, these show the margin boundaries. These both lines are called as margin boundaries. Now, you might be asking, why do we need to maximize this? Think about it. If you have a larger margin, that means you have a more breathing room. That means our classifier is more confident. If like a new data point comes in and there is a slight measurement error, then the large margin means we are less likely to misclassify it, right? If you take an example of data which is like this, and now let's say this would be your classifier, line classifier. Now, of course, the margin on the left is this, the margin on the right is this. Using this, if you were to classify a new point, let's say over here, this would be classified as an X instead of as an O. But if this was supposed to be classified like this over here, this would also be classified as an X. Why? Because we are not taking care of a place which is having a maximum margin. Basically, a larger margin means it has a better generalization way. The model is not fitting too tightly into the training data, so it will perform better on new and unseen data. That is the whole philosophy of SVM. Okay, so now that you know the meanings of both hyperplane and margin, now it's time to introduce the star of the show, support vectors. What exactly is this support vectors? As you've seen, the whole algorithm's name is called as support vector machines. What exactly are these support vectors? Support vectors are basically the points which lie on the margin. In this case, for this example, this is a support vector and this is a support vector. See these circle points? These are called as support vectors. And then the only things which matter in the support vector machines are only these points. Okay, you don't need to worry about all the remaining points. The only thing which you need to worry about are these points here, right here. But what about the other points? I don't need to worry about them. They can stay there. I can move them. I can delete them. I can add more. As long as I don't touch these support vectors, the hyperplane exactly remains the same. But even if I move the hyperplane, even if I move the support vectors slightly more, let's say I move this X here slightly below over here. Now your whole hyperplane starts to change. The hyperplane which used to look like this would now become probably like this. Why? Our support vector machine still thinks that, hey, the hyperplane which should be legal should be one which can have maximum margin between them. So as you change the support vectors, the margin changes, and as the margin changes, the hyperplane will shift. Okay, so these support vectors are literally supporting or defining the boundary. That's why in this algorithm we call them as support vectors. These are the supporting points for the boundary. Supporting points for the boundary. That's why they are called as supporting vectors. Now, this is powerful because in a data set with thousands of points, only maybe 10 or hundreds of them are support vectors. So the algorithm only needs to understand and remember these critical points so that it is very fast during prediction, and it is also very memory efficient as well. So let's just recap what we've seen so far. We've taken a look about hyperplane. Hyperplane is basically the plane which divides two classes in a model. Uh, the hyperplane divides classes. It's a plane which divides classes, and then margin is the maximum distance between a hyperplane and one of the support vectors. Okay, and then what is a support vector? Support vector is something which will support and make sure that the hyperplane has maximum breathable margin. Okay, so we got our fundamental concepts. Now let's just take this into action with a real example. Okay, now let's work with the famous iris data set. So basically this data set has flower measurements, petal length, petal width, sepal width. So for simplicity we are going to focus on just two features, petal length and petal width. So let's just get this data set imported. Let's just import numpy as np. Let's just import matplotlib.pyplot as plt so that we can visualize whatever we're trying to see. And from sklearn.datasets, import load iris. Now let's just take the data, which is iris is equals to load iris. And let's just take the data of x. X will be the data where we will just take the first 100 samples from this data. So that would be colon 100 from 0 to 100, and only the petal length and width. So that would be 2 to 4. Okay. So this would only consider second and third columns. Now let's just take the target value as well, which is iris.target, and then take the first 100 values from here as well. Okay. So let's plot the data. Basically, what we are trying to do here is we'll be plotting the data between the iris setosa and iris versicolor, and it looks something like this. We are just trying to see where iris setosa is here and iris versicolor is here. So if you want to separate these both using a support vector, something like this would be a better job in this support in this there. So see, there you go. Like the light blue points here are iris setosa, and darker blue points are called are iris versicolor. Now Now that we've seen the plotting here, let's just let me just show you what makes this SVM actually special. So in order to classify these two classes, I can draw many lines like this, like this. So I can draw many lines like this. But take a look at these both lines right here. Take a look at this line, the one which I'm highlighting right now, and take a look at the other line, which I'm highlighting in blue. Now, these both line, the one which is highlighted in blue is very close to the versicolor class. But the one which is highlighted in yellow, let me just move that point slightly. So now the yellow color highlighted line is lying exactly in the middle of both of them. Yes. Now, let's just consider these both lines for now, and let's see which of these lines do you think is a better representation of a decision boundary? How do you make that decision? So you make that decision when you come into consideration of the testing data, where they will separate the training data, but when it comes to the new testing data, you have to see that these tight boundaries between these lines, like look at the distance between this line and this point, and this line and this point. So this tight boundary over here might be risky because one class which is slightly above in this direction will be classified as iris setosa, but it is very closer to the ones which are in iris versicolor. So when new points come in, these tight boundaries will be very risky, and then small variation like this would cause misclassification. So in places like this is where we'll use SVM a lot. So what SVM does is SVM will find this line right here, which has a maximum margin. Now, what is margin? We've discussed about this already. Margin is basically the distance between the hyperplane and the support vector. So it'll find a perfect line. Let me just remove this. So it'll find a perfect line so that the maximum margin of this line to the support vectors is maximized. That is why we call SVM as a large margin classifier as well. Now let's try to code this up. I'll show you how you can do this in code. We'll train an SVM and visualize the decision boundary, and we can get a margin. So from sklearn, you can from sklearn.svm, you can import the support vectors classifier SVC, and from sklearn dot preprocessors preprocessing, you can import standard scalar. Now let's just create the standard scalar object, and let's just use our x value to scale it, fit transform x. So basically what this does is it will create a standard scalar object, and then you can use that standard scalar object to scale your values to lie in a certain range so that it will be easier for SVM to classify them. Now let's just put this in a separate code line so that we'll be able to see it properly. And we'll just train a SVM as well with a linear kernel. Don't worry, we'll talk about what this kernel is as well. SVC kernel is equals to linear and C is equals to 1.0. We'll talk about what these are. Okay, there we go. Our thing is created. Now let's just create a mesh. I'll just do this quickly for visualization. All of this is just for visualization. Now let's make the SVM predict on this. And now finally we can show the plot. So basically I've created an SVM model on this above data set. I've written the code for it right here. And this is how it would look like. Beautiful. Look at this. Like the solid black line here, this is called our decision boundary. And the dashed red and blue lines on the both sides will show the margins. And you see those red color circle dots over here? These are called our support vectors. Okay. So you can see that only a handful of these points are support vectors. Two from this side and two from this side are the support vectors. Now, these are the only points that define this boundary. This black color line, whatever we're drawing, these four are the only lines which define these. And if you look at the margin, you can see that it is a maximum margin or maximum margin. Okay, so you can think of it like a street. We can fit between two classes. You can think like it's we're laying down a road between two classes, and we want the widest road between them. Okay, now we've been talking about the straight classification, linear classifiers, but what happens if the data is generally not linearly separable? Like, what if we need like a curved data? What if we need like a curved representation? What if we need something which can divide our data, which looks like, which can, our hyper, in where our hyperplane looks like this? In that case, what can we do? So, take a look at this pattern right here. Now, in this pattern, you can see there's yellow points on the center and there's red color points around them as a ring. Now, let's see if you can try to separate them with a straight line. You can't separate them like this. You can't separate them like this. You can't separate them like this or like this or like this. Yes, but what have we talked in SVM? We've seen that it's a hyperplane which separates them. A plane can never bend, right? You don't have a plane which can bend. There's no plane which can bend. The planes every time will be in a straight line. True. So how do we exactly try to fit this? Because it is impossible right now. Because no straight line can separate these classes. So we'll need something like a circular decision boundary, which you can see right here in the blue color line. Sorry, green color line right here. You can see that we would need like a circular decision boundary. So how would we take care of that? How does SVM find this? Like, are we stuck here because SVM only does straight hyperplanes? No, that's not the case. Because in this case, there's a brilliant solution called as a transformation. Now, what exactly do you mean by transformation? So, we are aware that we can't separate the data in this current space, in this 2D space. So, let's just turn it into a 3D space where it becomes linearly separable. We'll just turn it into some higher dimensional space where it becomes linearly separable. Okay? We won't be able to separate this using a hyperplane in 2 dimension. So, why not convert it into some other dimension, third or fourth dimension, add my own dimension, and make sure that I can separate it over there. So let's say we have these two features. We have X and we have Y. Now, what if we add like other feature Z? Let's say Z is a function of both X and Y. And for this circular pattern, we'll use a function called as a radial basis function. Okay. Now, we'll use this radial basis function. Basically, it's like the distance from origin. So we can write Z as the square root of x square plus y square. So if you have any point x and y, you can easily find z with the formula under root of x square plus y square. Actually, you can skip the square root because we only care about the separation of these points, not the exact distance. So that would just make it z is equals to x square plus y square. Now, watch what happens when we plot this 2D points in our 3D data using this z value. Now you can see this data representation above, which we have seen over here, just by just adding this z value, we have converted into something which looks like sort of a cone. Okay, you can see these the points in the center, the yellow points in the center have become like a smaller cone over here. I'll just use black color so that I can show you. The smaller circles have become like a cone over here, which represents these points, and the larger circle outside has become like another base of a cone outside. Yes, we have just used another transformation. We've just added another axis. Previously, our data was in x and y axis. Now we have added just another z axis. Now, how do we correspond this z axis to x and y? That is using this formula, x square plus y square. Now you can see all the points have the points in yellow have the smaller x and y values. So x square plus y square is also small, so they just stay near the bottom. And the red color lines on the top, they have larger values. So the the red points in the ring will have larger x and y values, so they come upwards. Now you can see that they're like a cone, and you can easily separate them with a flat plane. Yes. Now, why is this a plane? I've told you this earlier. In an n-dimensional support vector, we will always have n minus 1 dimension plane. Okay. In this case, in 2D support vector, in 2D data, we had a one-dimensional, that is a line as a support vector. But in case of 3D data, we'll have a 2D 2D hyperplane, which is a plane. But if you look at this in the 3D space, this projection looks like a plane. But in the case of 2D, when we convert this back into 2D, the plane almost looks like a circle, one which is dividing the thing like this. Okay, so just for linear separability, we can name it as a circle. Okay, basically it's a plane passing through this cone, but since we only care about the place where this is being divided, we'll consider it as a circle. Think of it like a dissection point of the circle right here. Okay, So that is basically what we're doing. But you might be wondering, hey, in this case, this is a simple example. We knew exactly what transformation we used. We used x square plus y square. But in real data, how would we know exactly what to do, right? There might be different transformations. See, for 2D data, what we can do, we have polynomials up to degree 2. Like we can have features like x, we can have y, we can use x square, we can use y square, we can use xy, all of these. That's like 5 features over here. Okay. Now if we can combine these features, so if you're trying to convert 2D into 3D, you can use combination of these 5 features. Like how many would that be? It would be 5C3, which would be 10 ways. Okay, you have 10 ways in which you can have that as a third dimension. Plus, you can have a lot of linear combinations as well of these. Let's say you can have a combination as z is equals to 4x square plus 7xy plus 13y square, or something like 8xy plus 17y square, or 3x square plus xy, something like this. Create multiple linear transformations like this, and you can write your z value as any of these. Any of these would work. No, that's just with degree 2. But with degree 3, when we talk about third degree, you'll come across all the stuff like x cube, y cube, x square y, xy square, all these combinations. And again, through these linear combinations, all these kind of things will explode. So uh, let me show you like the frustrating thing about this. If you have a very complex data set, you can first attempt to do x versus y, xy features, and then you can do x square y, xy. So basically, you're trying to make an educated guess right here, right? I think the problem with this approach is quite clear. We need to visualize the data, and by the way, visualizing only works with 2D and 3D. You cannot visualize 4D data. If you have a four-dimensional data, that means a data which has four or more features, it's very hard to represent that as well, right? And then we need human intuition to guess good dimensions, good transformations. And then even with that, we might need many attempts. So basically, time complexity would be very, very high for all of these kind of simple transformations as well. So is there any better way? Is there any better way in which we can separate these both classes in this way? So yeah, there is, and that is called as the kernel trick. What exactly do you mean by this kernel trick? Because transformation is usually very expensive. Let's say you have a 2D point. Let's say I have a 2D point x comma y, and you want to transform this into something which has a higher degree. Now, what would be the features you will take care of? You'll take care of features like x square, you'll take care of features like y square, x, y, and constant, right? All of these you might be using them. Like you can just use 6 different kind of combinations just from 2 dimension. Okay. So if you want to compute, let's say x square, you have to use one multiplication operation. Yes. If you want to do y square, you can use one multiplication operation. You are computing xy, use one multiplication operation. So that's 3 operations. Okay, that's 3 operations just from degree 2. Now, let's say for 10,000 data points, if you have 10,000 data points, using these 3 operations on these 10,000 data points would be something around like 30,000 data points. Yes, just to transform them. Okay, and then you need to compare all the pairs of different points from this simple one point of that with another point x2 y2. Okay, that would be another 10,000 into 10,000 operations. So it's like 100 million comparisons you have to do. Okay, and then this is just in the case of 2D planes. If we take a plane of 6D, then each of these, instead of being three, it would be like 6 multiplications, and then it will be around 600 million operations. So I think you get the most idea about what we're trying to do over here. Okay, so, core insight about this kernel trick is that SVM doesn't need the product between those transformed points. You don't need to transform the points completely, like we've seen above. You don't need to transform these points completely into Z and then be able to find the actual plane. Instead, you just need the dot product between the transformed point and the actual points themselves. Okay, I'll just show you this with math. So without kernel trick, what were we doing? We were taking the value, let's say x, there's a point x 2 comma 3, and there's a point y 1 comma 2, and let's say we are going to transform this value of x so into, let's say it is x1 square and square root of 2 into y1 into y2, and let's say y2 square, something like that. And if you try to compute this for x, you would get it as, let's say, 4, 8.49 and 9. Okay, now let's just do the same transformation. Let's say you're transforming your y values as well into y1 square, square root of 2 into y1 into y2, and y2 square. Then your computation would be resulting in something around 1, 2.83 and 4. Now, if you were to find the dot product of these both computed stuff, phi of x dot phi of y, it would be, what would it be? It would be 4 into 1 plus 8.49 into 1, 2.83, and plus 9 into 4. Yes, this would lead to, like, let's say 64, around 64. Okay, now, to transform these both points, what did we have to do? We have to transform these points, and then we have to find the dot product. So totally, you would have to perform around uh, 1, 2, 3, 4, 5, 6 operations over here. You would have to perform 6 operations, that is multiplying here, and multiplying here. So 2, 4, and 6, and operations for each. And then you have to find the dot product as well. That is 6 multiplications over here, and two additions over here. So that would be around like 11 or 12 operations which you have to perform. But with kernel trick, what we can do is, let's say we are using some kernel called as a linear kernel, polynomial kernel. Okay, let's just take a polynomial kernel. Now, what is this polynomial kernel? You can just say, hey, it is a function of x comma y where we can just multiply the values of x and y together and square them. Okay, so basically dot product of both of them, dot product of x and y, and then just square them. So let's just see how much this takes. So let's just take the same values. It will be 2 into 1 plus 3 into 2 whole square, which is 8 square, which is 64. Now you can see we got the same answer, 64 over here, 64 over here, but we did it with way less work. Okay, we did two multiplications, we did one addition, and then one square. Okay, it's the same answer and it's doing way less work. Now, why is this called as a kernel trick? Why is this a trick? Because you'll get a dimension of a high, you'll get a benefit of doing it in a higher dimension without actually transforming it anywhere. Okay, all you're trying to do is just doing the dot product in the lower dimension itself, but you're getting the dimensional benefit of higher dimension space. Now, if you don't use kernel trick, mathematical products and everything would be have to be performed in higher dimensional space, and it would be very hard work. You have to transform, you'll have to do the higher dimensional storage, etc., etc. So this way it is way easier to do it. Now here we've seen a example of polynomial kernel. Now there's some other kernels as well. One of them is called as a linear kernel, and one of them we've just seen now, polynomial kernel. The other one is radial basis function, which we've yet to discover, or this is also called as Gaussian kernel. And one of them which is most used is called sigmoid function, sigmoid kernel. So yeah, let's just go through this one after the other slowly. What does linear kernel do? It is nothing fancy. It is just a regular dot product, x dot y. And when do you use this? You use this when data is already linearly separable. Like, let's say you have a spam classification with word frequencies, that data is linearly separable. So you can just do the dot product of both of them and you'll be able to find it out. What is polynomial kernel? We've just seen it. We'll be using some kind of degree. Here we have used x dot y whole square, but it usually is in the form of x dot y plus c power d, something like this. So that if d value is equals to 2, then we'll have quadratic relationships. If you have 3, it will be cubic relationship. It's implicitly used for polynomial degrees so that the relationships are in polynomial. So yeah, next one is radial basis function, which we're going to see as well. It measures this similarity based on the distance between the 2 points. It is given by e to the power minus gamma x minus y whole square. This is the formula of a radial basis function, and it is usually used for similarity based on distance. And so whenever the value of x and y are closer, then this value will be closer to 0, right? This value will be smaller. If x is almost equals to y, this value will be closer to 0. If this value is closer to 0, e power minus something value will be lesser. Yes. which will be somewhat similar to e power minus something will be similar to 1. Okay. Okay. That means the value would be very similar and it would be closer to 1. But if x and y are very farther away, then that means this whole value will be much larger. If it is much larger, e to the power minus something which is much larger is very close to 0. That means both of them are not similar at all. So the graph of this would look something like this. It would look like a bell curve over here. The radial basis functions thing would look like a bell curve. So uh, the distance sorry, this is the origin, this is the distance, and this would be the similarity. Sorry, it would not look like this. It looks something like this. Okay. Now, as the distance increases at one point, you will be able to see that, hey, it is much similar. The similarity score keeps increasing. But after a certain distance, the similarity score starts falling down. Now, what is the sigmoid kernel? Sigmoid kernel is basically given as a tan h function. Basically, it mimics like a neural network activation function. You don't need to know much about this. When you want your SVM to behave like a neural network, you can use a sigmoid function. Let's just take a look at this radial basis function because this is the most used function in SVMs. So we've seen this. So let's just write the formula down again. Let's say there's 2 points, x and x prime. Okay, and the formula is given by uh, e to the power minus gamma into the distance between x and x prime whole square. Okay, this is called as a radial basis function. Now, what exactly is the use of this radial basis function? You might ask. Basically, gamma here is a hyperparameter. Again, if you don't know what hyperparameter is something which the developer can fine tune in a machine learning model. And if the gamma value is very small, then this will become closer to zero. And if this is closer to zero, e power value will become a wide gentle curve. So your curve will become like this. In that case, your curve would become more like this. But if the value of gamma is very huge, then that means this value will become very huge. E to the power minus that value would become extremely small, and so that your curve would become very, very steep like this. So large gamma will create a narrow and steep curve, and smaller gamma will create a wide and gentle curve. Now I'll show you this with code so that you can visualize how three different SVMs with three different gamma values will be trained. So onto the coding screen. Now here in this case, we've taken three gamma values, 0.1, 10, and 100. So let's just see. With 0.1, as you can see, the boundary is very smooth. Okay, it's almost like linear. Okay, the model is underfitting slightly, but it is able to generalize it well. It is able to see that, hey, this is going it like this. But in the middle plot, we've seen that gamma value is 10 now. And now we're getting somewhere. We're able to see that, hey, the boundary is slightly looking like a crescent moon. Okay, and it's you can say that gamma value 10 is like a perfect, properly fitting model. But now, as you can see at right side, now the gamma value is 100. Look at those pockets, or look at those accurate representation like this. Okay, in this case, you can say that, hey, this is fitting every single training point properly. That means it is overfitting the model, and due to this, it will perform poorly on new data. Let's say you have a newer blue point which is supposed to go here, but since it's in the red zone, it would predict that as a red point. Why? Because it has learned the data so well that it is overfitting. Okay, so why not always use this higher gamma values? Because higher gamma values will always lead to overfitting. Okay, model will become too complex, and it'll learn the noise as well in the data instead of actual pattern. So if you have smaller gamma values, it will be almost linear. So as you can see, 0.1, almost linear, almost a straight line, and it might underfit. But if you have a larger gamma value, it is highly non-linear, so that it might overfit. So you have to find the optimal gamma, which is just right, so that you can have a just generalization. So basically, in this code, I fit three different gamma values. As you can see, three different SVM models with three different gamma values. So I've just used that to predict. The code for prediction and code for everything is as same as the previous ones. If you haven't seen my k nearest neighbors video, I've shown you guys how you can use this sklearn. The code is same. All you need to do is just use svc instead of the k neighbors classifier. So if you haven't watched that video, go watch that. It's very cool. So basically, kernel trick is one idea where we can get the power of an infinite dimensions transformation just by looking at the function, the cost of a simple function. Okay, now we need to talk about a major limitation we have been ignoring all this time. So everything I've shown you so far assumes that we can find a perfect separation. Uh, we can find a perfect separation between these 2 points. Let's say you've taken this data set itself. You are just assuming that, hey, we can find a perfect line between them. But what if I were to add, let's say your real life data would have a lot of noise in them, right? So what if in that noise, let's say there is a class which shows, hey, this is iris versicolor, but the circle is shown here. In that case, if you were to train an SVM model and you were to see the support vectors, this would be one of the support vectors, and this would be another support vectors, and the hyperplane would be something like this. Yes. Now, is this a good hyperplane? Absolutely not. It's not a good hyperplane. Why? Because if there is a, let's say, a new point which is supposed to be going here, it will incorrectly predict that as blue, iris versicolor, instead of being iris setosa. Why? Because we are saying that, hey, it lies on the other side of the margin where iris versicolor is there. So, hey, this is iris versicolor, not iris setosa. But in reality, it lies within the cluster of iris setosa. Okay. So, this creates a problem. Okay. Now, this margin, which is perfect, which will use the support vectors as it is without considering any error, this margin is called as a hard margin. Okay. This margin is called as a hard margin, and basically hard margin classification will say all points must be on the correct side of the margin. There's no exceptions and no violations. Okay. Just if you have one outlier, it will mess the whole model up. Now what is the solution for this? What do we need to do? Now the solution for this is a soft margin classifier. Okay, what exactly is a soft margin classifier? In soft margin classifier, instead of demanding like perfection, we'll allow some mistakes. We will allow some mistakes, but we'll make sure that we'll punish the model as well, so that it doesn't make that mistake as well. So we'll take a look at this boundary. We'll keep this point. Let's just add another point as well for the other color. So if you take this line right here, okay. So this performs a normal generalized way. It is generally a good way, even though it will like misclassify one or two outliers. If you generalize it much better. So basically, soft margin classifier will make sure that, hey, even if there's one or two outliers in my model, I'll try to ignore them and still construct a hyperplane. But I'll make sure that I penalize the model in such a way that I will not be overwhelmed by the outliers. Uh, if that is clear, we'll try to see what this how the soft margins work. Now, soft margins will introduce another hyperparameter called C. Now, we've seen this while coding. What does this C exactly do? I'll tell you. C will actually control the trade-off between margin width and classification errors. So basically, that means if you have a very high value of C, that means, hey, I don't want to misclassify anyone. Okay. I don't really want to misclassify anyone. So I'll just make sure that, hey, my margin is very narrow. So I'll just be able to show something like this. Something like, hey, something like this would be a margin for me. So it doesn't care about the margin. I'll just remove all these other lines so that it's very clear for you. It doesn't care about the other lines. It will just see, hey, I don't want to, mess around with these. I don't really care about these outliers. So I don't really want to, misclassify anyone. My blue point is there. My this point is there. I don't care about the margin. All I want to do is do a perfect line. Okay. But if you take the value of if you take the value of C as very high and look at this, it's very close to both the classes. Okay, and this is very close to hard margin. Okay. Now, this will most likely overfit the model. Why? Because we don't care about trying to generalize the model. We are trying to care about fitting the data perfectly. That will learn. We are basically telling the model, we are letting the model learn about it. So C value, very high C value will make sure that the model will overfit. But if even if we take very less C value, like let's say the C value is like 0.01 or something, then we're allowing the model to make a lot of violations. Like you can say that the model will take this as a hyperplane as well. Okay, this is not true. This is not true as a hyperplane. It will make too many violations. The model will become too simple. The model will become underfit. Okay. So a good margin with a fewer violation stays reasonably far from both the classes. So this would be like a sweet spot where you need to find the exact value of C. Again, this is a hyperparameter. You have to keep testing based on your data. So now let's take a look at how the C value affects different kind of affects the data based on the value of C. So let's just switch to the coding screen. So here, let's just see the value of C based on the value of C. uh, yeah, as you can see, look at the progression we've made. Okay, with C value 0.01, we have a wide margin here, but we have a lot of this as well. So let me just comment this yellow color circles so that we'll be able to easily look at the points. Yeah, see, as you can see, with this wide margin, we have a lot of violations with 0.01. We are just saying the model, anything is fine, just draw a hyperplane. So I just made a line at, x is equals to 0 and plotted them and say that, hey, this is my hyperplane. But if we take c is equals to 100 as well, you can see we have a narrow margin. This margin value is very low. I know it is indistinguishable, but basically this margin value would be very low and very few violations, and it would be overfitting for the training data. Now, C is equals to 1, something like this. You have to keep trying out different ways to make sure that you get a proper value so that you can have many number of support vectors in order to classify it properly. Now, I want to show you a simple implementation of SVM from scratch. Now, this isn't like a production ready code, but it'll basically strengthen your understanding about it and what is actually happening. But if you want to code this out, just let me know in the comments below. I'll make another video telling you how I've coded this from scratch. But for now, all I want you to know is I've created an SVM class over here. So sample SVM, I just made this sample SVM class over here, and then I've created my own data over here from x test y test, and then I've trained our model, fit it, and compared it with the actual model. Again, using it with sklearn is very easy. You can just do from sklearn.svm import svc and just create a object, use a kernel, whatever kernel you want, and use the c value properly. We've seen about both of these, and then do dot fit. And yeah, as you can see, both of them we have 100% accuracy. Of course, the actual sklearn implementation will use more sophisticated optimization algorithms, but the core idea is almost the same. Okay, so if you guys want me to code this with you while explaining everything, make sure you comment down in the description. I'll try to make another video on that. Right now, so where exactly are these SVMs actually used? So let's just talk about some real world applications. Okay, so SVMs basically they're used in image classification models. Okay, so SVMs are very good at recognizing handwritten digits or faces and objects. And in fact, before deep learning, SVMs were used for image classification, and you can use SVMs for text classification as well. Okay. You can use SVMs for medical diagnosis, financial forecasting. So basically stock market predictions or credit scoring, fraud detection, etc. Or you can use them in other domains like geosciences or computer vision, self-driving classes, self-driving cars, etc. So you have a lot of these. And why exactly do we prefer SVMs? It has three main reasons. First is it is so three main reasons. First is it is very effective in high dimensional spaces. It is very effective in high dimension spaces. Why? Because even when dimensionals exceed the sample size, even when there's many dimensions as well, you can always create a function which will generalize this SVM approach. And the second one is it is memory efficient. Why? Because we only care about the support vectors, not anything else. And finally, it is versatile as well. Okay, that means you can use different kernels for different problems, different kind of data. Okay, so let's just recap what we've seen so far. We've seen the fundamental concepts of SVM. We've seen what hyperplanes are. We've seen what margins are. We've seen that SVM is called as a maximum margin classifier, and it will stay as far away from both the uh, both the classes as far further away as possible. And we've seen how the trick helps us to handle nonlinear data. We've seen that over here. And yeah, we've also seen how you can code up SVM. We've seen different values of C. We've seen how different values of C affects it, how different values of gamma in the radial basis function affects the SVM. And yeah, I hope this gave you like an intuitive understanding of how SVMs work and why they are so powerful. But if you want to go deeper, I will put all the code examples and additional resources you can find down in the description below. And yeah, if this helped you understand SVMs, please make sure to go give us a like, give us this video a thumbs up, drop a comment if you want to if you want me to make any other videos, or if you have any other questions, or if there's any other algorithm you want me to explain. And subscribe for more machine learning deep dives, deep learning. I'll be making more AI, generative AI videos as well. So, yeah, thanks for watching, and I'll see you in the next one.